Hello, everyone. Good day, good afternoon, good morning. You are now listening to us presenting our chemistry behind the V6 engine. It is our in-depth discussion behind the V6 engine, which is shown in this car right here, which is actually a Ford GT, one of very beautiful car, especially in yellow. And yeah, it has a V6 engine. Now we're going to be talking about more in-depth discussion about its chemistry. Here are our group members. We are Compass Group, and we are the group three of chemistry. Now, allow me to introduce ourselves. I am Joshua Miguel Aguilar Peregrino, your engineer, and also my partner here, which is Engineer Tobias Giles Dahan. We also have our researchers, which is comprised of Shana Micaela Garcia Labo and Mark Kian Quintanangkin, which are assisted by Mr. Brian Dave Tan Alojado and Mr. Greg Christian Ciencia Carvalho. Now we're going to be first talking about the part one, which is the main concept of our engine, which is going to be discussed by Miss Shana and Mr. Tobias.
There are many types of gasoline engines, but at their core, all engines revolve on a very simple principle that involves capturing energy from a rapid and continuous sequence of small and controlled explosions and using that energy to propel a vehicle. A common type of engine is the V6 engine. They have been offered in cars since the earliest days of automobile production. In fact, it was a popular choice for many types of cars and trucks since the 1960s. The Marmon Motor Car Company was one of the earliest pioneers of V6 engines. In 1962, the Buick LeSabre became the first American production car to use a V6 engine. And today, V6 engines are among the most produced, designed, and built by major automakers.
As you can see in the picture, the V6 engine got its name due to its V-shaped arrangement of the cylinders. This is because it uses a single crankcase with two banks of cylinders attached, in which a common crankshaft is driven by all six cylinders. V6 engines are measured in terms of the angle at which the cylinders oppose one another. Many V6 engines uses a 90-degree mount, while others use an acute angle for a more compact design, like the VR6 engine. Furthermore, since each side of the engine contains an odd number of cylinders, the engine is not naturally balanced. While two cylinders fire on one side of the engine, only one cylinder fires in the opposing bank.
So now we're going to be talking about part two, which is the thermodynamic principles, which is going to be discussed by yours truly and my partner here, which is Mark Kian. So, first, a V6 engine is a six-cylinder internal combustion engine, and it is a type of heat engine. And it converts the energy from the combustion of gasoline into mechanical work. So that is the main thermodynamic principle. So here, heat, right? Combustion, heat, and then into work over here, the crankshaft, which is going to drive the wheels. That's the work. So also here is the engine stroke, which is going to be further discussed by my partner, Mark, over here.
The four engine strokes are as follows: intake, compression, combustion, and exhaust. The first process is intake, and as its name suggests, it intakes air to the engine. The second process is compression. So compression is where all the air that was accumulated from the first process will be compressed in order to produce heat. And with heat, combustion will take place. So combustion is the most basic chemical process of releasing energy from the air-fuel mixture. The air-fuel mixture is important because with air-fuel mixture, it burns, the oxygen will burn the fuel completely. And with that, a spark will happen naturally. And the last process is called exhaust. So all the gases that was produced by the three processes mentioned earlier will be swept away in the exhaust. And with that, it makes a new area for the new air that will come to the engine.
So thank you,
The
Mark,
four
for that explanation on the power strokes of the engine. So here is the engine systems, and here is the octane rating, which is fourth. And then although this is an inline four engine and ours is a V6 engine, it still perfectly describes or visualizes for us what's inside, what's happening with the engine. So it's actually a really tightly packed system, and then simultaneously and harmoniously working together to create work for our wheels, which moves the wheels, which moves the car. So now, the next part is combustion reaction, which was first mentioned by Mark a while ago. So yeah, we have fuel, oxygen, carbon dioxide, and water. So the carbon dioxide, this one is the exhaust. Yeah, exhaust. So carbon dioxide and water. So it goes out of the system, and then fuel and oxygen goes into the system. So intake and exhaust, the two most important things in the engine. So now we're just going to highlight the heat and the energy. Actually, not really shown mostly in chemical equations, the heat and the energy, but it happens like all simultaneously with combustion, because after all, we need heat. We need heat energy to combust, to make an explosion. We need heat energy so that when it combusts, when that explosion creates, the carbon dioxide and the water would explode, and that movement will create energy. So that explosion will create energy, which pushes down the piston, and that pushing down of the piston will move the crankshaft, and that crankshaft will move the wheels. Yeah. So here is our bioethanol reaction, which is going to highlight heat and energy again. And then here we have fuel, oxygen, carbon dioxide, and water, which is just basically the combustion reaction. This is just the only difference, the fuel. Just, yeah. The first law of thermodynamics states that energy cannot be created nor destroyed, but it can be converted from one form to another, like, for example, the heat to energy. So I just highlighted energy here because energy can be taken into many forms, and then just put it into general form, because there are going to be two types of energy that we're going to be talking about in the next slides. So here is our PV equals nRT, which is the ideal gas law. But first, we're just going to highlight PV, highlight pressure and temperature. So pressure and temperature. So as pressure increases, the temperature also increases. And that is the main concept behind the compression stroke that Mark has mentioned earlier, the second stroke. So compression, it compresses the air and it increases the temperature. When increasing the temperature, the heat energy also increases. So yeah, although it cannot be created, the heat is not created, it's just gonna increase. So here we have the compression stroke. There, more energy, more temperature, so it makes it easier to combust if it's compressed. Now here we have the heat or Carnot engine equation. So the Carnot engine is actually a very efficient engine, and then it has 100% thermal efficiency. And then we're just going to focus on the heat engine because our engine is not 100% 100% thermally efficient. Now, Carnot engine would state that work is actually equal to QH minus QC. So QH is the hot reservoir, and then QC is the cold reservoir. So QH is the initial temperature or initial energy that we start with. So it comes into the system. Now the QC is what comes out of the system. So that's the final. So QH minus QC. So QH, QC. So in and out. But it's not just QC that comes out. There's also work that comes out. So it's not so energy comes in. For example, heat comes in to the system, and it goes to divide into two. We have heat and we have work. So heat is just useless, cannot be converted anymore. It just makes the engine hot. That's why when we touch it, the engine that's working, it's hot. And then work, useful energy, this one converts the energy into rotational energy, which moves the crankshaft, and then it moves the wheels. So yeah, here's the initial and the final energy. So we're just going to use the Mercedes F1 car, the current Mercedes F1 car, and then it has a V6 hybrid power unit. So this is the hybrid power unit, and it has 950 horsepower. We're just gonna forget about the 1000 because that one has help from the electric, so just use the 950. 710 kilowatts and then 52% thermal efficiency. Yeah, see, 52%. It's not 100% like the Carnot engine. Just take note of these three, and then we'll put the 52% because 52% of the engine, the thermal efficiency means that 52% of the heat gets converted into work. While the rest, if you minus that with 100, it will get 48%. So this is 48% will be converted into making the temperature of the engine hot. It makes the engine hot. So here we have horsepower. Initial, we solved initial by dividing it by 0.52. Then just doing the moving of the equation. And then, yeah. Here's the heat loss, 876 horsepower. So imagine na lang 800 horses are lost. 876, more than 800 horses are lost. That's a lot of kabayo. Next, we have the kilowatts, just the same. 710 work goes to the wheels. 1000 are the original energy that's input, and 655 kilowatts is lost. Now convert that to watts, multiply that by 1000, and then you get the watts, which is just actually joules per second. So joules per second, that's 1 million, more than 1 million, 1,365,000 comes in, and then what comes out is 644,000. And then 710,000 joules comes out of the wheels, and that's in every second. That's in every second. Now, in every second, that's 876 horsepower. So 876 horses every second are lost. 950 horsepower in every second is gained. And then here's the combustion reaction. So that's gonna create the horses. It's gonna do the horses, the power. Now, we're going to be talking about part 3, uses and applications, and that will be discussed by Mr. Brian Dave Alojado and Mr. Greg Ciancia Carvalho.
So, chemistry is everything and everywhere. Whether we are chilling in an air-conditioned room or riding a car, the application of thermodynamics is everywhere. Thermodynamics deals with the concepts of heat and temperature and the interconversion of heat and other forms of energy. Different types of vehicles such as planes, trucks, and ships work on the basis of the second law of thermodynamics. Thermodynamics is also involved in the study of different types of power plants, such as nuclear and thermal power plants. Another uses and applications of thermodynamics are the heat transfer concepts, which are widely used in radiators, heaters, and coolers.
Aligned with our product, which is the V6 engine, thermodynamics is hugely present here. Some high-end sports bikes and cruisers could feature a V6 or a VR6 engine layout. It is also widely adopted for medium-sized cars. It is commonly used in modern cars since the engine's space is used by a V6, which is much more compact and smaller than a V8 or an inline 6. As an addition, it gives more power than a traditional four-cylinder engine, and it is fuel efficient. More examples like the Ford Mustang V6, Ford GT, an Alfa Romeo Giulia Quadrifoglio, and a Toyota Land Cruiser GR Sport. And did you know the V6 engine was used by Formula One race cars on intense racing competitions?
So that is it for our short presentation. Thank you so much for listening. Here are our references, and then let's go. Thank you so much for listening. Humanata.